Our second graphing example is going to be a rational function. This one's going to take a little bit longer than the polynomial we did as our first example, so I'll break this video into two parts. First of all, let's get all of our pre-calculus information about this function. To begin with, we can talk about the domain. The domain is going to be all the numbers where the denominator is non-zero. So the domain is going to be all numbers except for 1. 1 has to be excluded. Range, once again, is something that we need to come back to. Let's look at asymptotes. Vertical asymptotes will happen if the denominator is 0 and the numerator is not 0. Notice that when x equals 1, the denominator is 0 and the numerator is equal to 4. So that's the location of a vertical asymptote. Horizontal asymptotes happen when the degree of the denominator is equal to or larger than the degree of the numerator. So here the degree of the denominator is less than the degree of the numerator. So there are no horizontal asymptotes. This function is, however, going to have slant asymptotes, which are also known as oblique asymptotes. So let's take a minute to talk about those. So oblique asymptotes, also known as slant asymptotes, occur when the degree of the numerator is exactly 1 more than the degree of the denominator. So here, the degree of the numerator is 2, the degree of the denominator is 1. So that means that we are going to have slant asymptotes. The way that you find the equation for the slant asymptote is you use either synthetic or long division to divide the denominator into the numerator. Let's use long division for this one. That's what will work in general. So let's take x minus 1 and divide it into x squared minus x plus 4. Dividing the leading terms, x squared divided by x is equal to x. So I'll write that x on top. I multiply x times x minus 1 and write the answer below. And then I subtract. To subtract this polynomial from the top polynomial, I need to distribute a negative 1. So I change the signs and then add. X squared minus x squared is 0. Oh, here the negative x and the positive x also cancel. And I end up with the 4 as a remainder. Very often there's going to be an extra term or an extra step in here before you get to a constant. So I'll write that remainder term as 4 divided by x minus 1. So what this means is that the original function, x squared minus x plus 4 divided by x minus 1 is exactly the same as x plus 4 over x minus 1. These are identical functions. Now to get the equation for the slant asymptote, we discard the remainder term. So for the slant asymptote, that's going to be y equals x. I'll talk about what it means to discard this 4 over x minus 1 once we draw a possible graph for the function. So this is the equation for the slant asymptote. And then the remaining information we can get using pre-cal is we can get the x and y intercepts. So to get the x-intercepts, we're going to set the numerator equal to 0. So that's x squared minus x plus 4 equals 0. We can't solve that by factoring, so let's use the quadratic formula. We'll have negative b, so positive 1, plus or minus the square root of b squared minus 4ac over 2a. Notice that when I simplify what's under the square root, I get negative 15. So that means that there are no x-intercepts. So this graph's not going to touch the x-axis. And then finally, for the y-intercepts, we set x equal to 0. And that'll give us f of 0 equals 4 over negative 1, or negative 4. So the y-intercept is 0, negative 4. Let's see if we can put all this information together in a graph, at least as our first guess at what's going to be the graph of the function. So we have a vertical asymptote at x equals 1. We have a slant asymptote with equation y equals x. We have no x-intercepts, and our y-intercept happens at 0, negative 4. So let's just say that this is negative 4 on the y-axis. But this is really enough to go ahead and get a pretty good graph of the function. We know that the graph has to cross the y-axis down here at negative 4, but it also has to respect these two asymptotes. So going to the left, it needs to approximate the slant asymptote. And going to the right, I suppose that it could either go up or down this vertical asymptote, but we know that there are no x-intercepts, so it can't cross the x-axis in here. So that must mean that it dips downward. Now to the right of this asymptote, for one, we see that the power on the x minus 1 in the denominator is odd, so that means that the graph will jump from one side of the asymptote to the other. So we can kind of sketch in what the graph looks like over here, respecting the two asymptotes. Another way to get this is we could observe there are no x-intercepts, so the graph can't come in from below. Or, if you wish, you can simply take a number like 2, substitute it in, and you'll see that you get a y-coordinate, which is positive. So this is our best guess at what the graph is going to look like. Now, about this 4 over x minus 1, the graph of the function, if I want the exact y-coordinate for a given x, I could plug it into x plus 4 over x minus 1. That'll give me the exact y-coordinate. However, notice that if x is really large, then 4 over x minus 1 is going to be a really small number. So for example, if I plug in 100, then the y-coordinate is going to be 100 and 4/99. So notice that 4/99 is really small compared to the 100. So if I look at the graph, here's going to be the 100, and then 4/99 is going to place the graph just a little bit above that. So the graph is going to be just above y equals x. And the larger that x gets, the closer the graph is going to get to that asymptote.